Hey everyone, welcome back to the channel. Have you ever worked with a massive dataset and found yourself waiting, and waiting, and waiting for your pandas operations to complete? Maybe you've gone to grab a coffee, come back, and your code is still running. Yeah, I've been there too. Today, I'm going to show you something that completely changed my workflow: how to speed up pandas by up to 20 times using GPU acceleration with almost zero code changes. This is something I recently used in the IBM SkillsBuild Hydropower Climate Optimization challenge on Zindi, and the results were honestly mind-blowing. So, if you're tired of waiting for your data processing tasks and want to supercharge your pandas workflow, stick around because this could be a game changer for your data science projects. Let me first give you some quick context about this competition. The IBM SkillsBuild Hydropower Climate Optimization Challenge is focused on predicting energy load generation for micro-hydropower plants in Pakistan's remote Kalam region. These plants are the primary energy source for rural communities, but they face challenges with fluctuating water flow, maintenance issues, and weather impacts. Our task was to build a model that could accurately predict energy generation in kilowatt-hours based on a variety of factors. Sounds straightforward, right? Well, not when you're dealing with 39 million rows of data that take up about 5 gigabytes. That's where the real challenge began. When you're working with datasets this size, standard pandas operations become painfully slow. And as data scientists, we need to be able to iterate quickly, testing different approaches, exploring the data, and refining our models. Waiting minutes or even hours for basic operations creates a massive bottleneck in our workflow. The competition had a time limit, and I was spending way too much of that precious time just waiting for data processing. There had to be a better way, and that's when I stumbled upon Rapid's cuDF. So what exactly is Rapid's cuDF? It's a GPU dataframe library that provides a pandas-like API, allowing you to process data on your GPU instead of your CPU. The really cool part is the cuDF pandas feature, which acts as a drop-in replacement for regular pandas. What does that mean? It means you can take existing pandas code and accelerate it without having to rewrite everything or learn a new API. One line of code before your pandas import is all it takes to start using your GPU for data processing. According to NVIDIA, their benchmarks show speedups of up to 150x. In my own testing with the competition data, I consistently saw 10-20x improvements, which is still absolutely remarkable. Let me take a minute to explain how this magic happens behind the scenes. When you enable cuDF pandas, it essentially creates a proxy module that intercepts all your pandas imports. When you call a pandas function, cuDF pandas tries to use an equivalent GPU function to execute that operation. If it's successful, you get the speed benefit of GPU computing. If it's not supported, it temporarily copies the data to the CPU, processes it with regular pandas, and then returns it to the GPU. The end result looks and behaves exactly like a pandas data frame, but many operations run significantly faster. It's really the best of both worlds. You get GPU acceleration without having to learn a new library or rewrite your code. If you want to dive deeper into how it works, I've put a link to the Rapids documentation in the description below. So how do you actually use this? It's incredibly simple. All you need to do is add one line before importing pandas. That's it. After that, you can use pandas just like you normally would. When you read a CSV file or perform filtering operations, they'll automatically use the GPU when possible. Of course, you'll need an NVIDIA GPU and have Rapid's cuDF installed. If you don't have a GPU in your system, don't worry, you can use Kaggle notebooks with their free T4 GPU runtime. That's what I used for the competition, and it worked perfectly. Now let's look at some real numbers from my experience with the competition. When reading the CSV file, regular pandas took 53 seconds, while cuDF pandas did it in just 6.7 seconds. That's almost 8 times faster. For string extraction operations, which I needed to do a lot of, the difference was even more dramatic. Pandas took 1 minute and 23 seconds, while cuDF pandas finished in just 1.8 seconds. That's a 46x speedup. Filtering data showed similar improvements. 3.5 seconds with pandas versus 0.2 seconds with cuDF pandas, about 17.5 times faster. But here's where it gets interesting. When I tried to use date operations, I initially saw a massive slowdown. What was taking pandas 19.4 seconds was taking cuDF pandas 2 minutes and 28 seconds. That's more than 7 times slower. Why? Because I was using an operation that wasn't supported by cuDF, causing expensive fallbacks to CPU. And that brings me to an important point about potential pitfalls. Not everything in the pandas ecosystem is supported by cuDF yet. When I ran into issues, it was with date operations. Here's what my problematic code looked like. Imagine I have timestamps like this, and I want to extract just the date part. In the original starter notebook, it is done by using dt.date attribute. This works fine in pandas, but the dt.date operation isn't supported in cuDF. I found this GitHub issue discussing the complexity of GPU implementation of this issue. It is a popular feature request, but unfortunately it is not supported yet. When cuDF pandas encounters the dt.date operatio, it has to copy all the data back to the CPU, run the operation, and then copy it back to the GPU, which is extremely inefficient. What's worse, due to the unsupported date data type, the resulting data frame is on CPU, and the group by aggregation operation is also done on CPU. This and the data copying between CPU and GPU make it significantly slower than just using pandas. The solution was to use string extraction instead, which is GPU accelerated. This accomplishes the same thing, but uses operations that are supported by cuDF. The resulting data frame is also on GPU, and everything is fast. With this change, what was taking over 2 minutes now took just 1.1 seconds, a 17.6x speedup over even the regular pandas operation. Based on my experience, here are some best practices when working with cuDF pandas. First, prefer basic operations like simple aggregations, filtering, and transformations. These work best with GPU acceleration. Second, watch for operations that suddenly become very slow. That's usually a sign they're falling back to CPU. Third, always time your code to identify bottlenecks and compare performance with and without GPU acceleration. Fourth, for any unsupported operations, try to find GPU-compatible alternatives like I did with the date extraction. Fifth, if you're debugging memory issues, you can turn off unified memory management with this environment variable. This helps you monitor and manage GPU memory more efficiently during debugging. When I put all this together for the competition, the end-to-end timing for my full pipeline went from 262 seconds with regular pandas to just 149 seconds with optimized cuDF pandas, almost cutting the processing time in half. The benefits are clear: minimal code changes, significant speedups, compatibility with the existing pandas ecosystem, and seamless integration that falls back to CPU when needed. It's especially valuable for large datasets where pandas on CPU becomes a bottleneck. For the IBM challenge, this meant I could iterate faster, try more complex models, and ultimately produce better predictions. So there you have it. With just one line of code, you can dramatically speed up your pandas workflows using GPU acceleration. If you work with large datasets, this is absolutely worth trying out. I've put links to all the resources in the description, including the Rapids documentation, the NVIDIA blog post about the 150x speedup, and links to my Kaggle notebooks showing the baseline pandas code, the problematic cuDF pandas implementation, and the fixed fast version. If you found this helpful, please hit that like button and subscribe for more content on data science, machine learning, and competitive AI challenges. Drop a comment if you've used GPU acceleration for pandas or have questions about implementing it in your own workflows. Thanks for watching, and I'll see you in the next video where we'll dive into more techniques to supercharge your data science projects.